Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. In this video, I'll be showing you this concept of partial derivative. So we're going to basically look at this, how to find the partial derivative, and we're going to do some examples, inshallah. So let me just get the slides on. It's not that complicated because we're going to still be applying the same concept, the same formulas, the same rules with regard to derivative that we have discussed previously. So partial derivatives, because this is a continuation from our previous discussion when we dealt with function with two variables, x and y. So instead of having one independent variable, so now we have two independent variables. So partial derivatives. Partial derivatives, so we're going to consider functions that have two or more independent variables. So for this course, we're going to basically limit our discussion to two independent variables, x and y. Okay. So in the previous section, there was an example of a company producing surfboards, okay, that was discussed. And the cost function was given as 500 plus 70x, okay, for the standard board. Okay, the standard, because the company produced two types of surfboards, standard and the competition. Now the derivative of this cost function would give the marginal cost function for the standard board, which is 70. Okay, 70. Since this marginal cost is constant, it is constant. So $70 is the change in cost for every 1 unit increase in the production, regardless of the output level, because this is constant. This is constant. For a company that produced two types of surfboards, a standard model, we have two models, standard model and competition model. The cost function was the multivariable function C of x and y. Okay, C of x and y, where x is the standard, okay, x is standard, while y is the competition model. So the cost, okay, so the cost function was given as 700 plus 70x plus 100y. Okay, if we differentiate this cost function with respect to x, treating y as a constant, in other words, we are holding y to be fixed, so we're going to denote the resulting function, the first derivative of the cost function with respect to x, as c sub x. Okay, so this is what we term as c sub x. If we differentiate this cost function with respect, so if we were to differentiate this cost function with respect to y, holding x constant, okay, then the resulting derivative is denoted as c sub y. C sub y. Okay, so this derivative would be, so if we were to do that for the first one, when we differentiate this cost function with respect to x, we're going to have 70, right? This is 70 because we are holding y to be constant. So when we treat y to be constant, it is the same as 700. So there is no x here, so this becomes 0 and this becomes 0. What about this one? When we differentiate the cost function with respect to y, so this becomes 0, this becomes 0, and this becomes 100. Okay, so this is the derivative. So this is what we term as partial derivative because we only differentiate the function partially with respect to one variable only. And in this example, the partial derivative basically represent the marginal cost of x and the marginal cost of y. Okay, the increase in cost when we increase output of standard model by 1 unit is $70, and the increase in cost when we increase output of competition model by 1 unit is 100. Okay, so in general, if we have this function z is a function of two variables f of x and y, then the partial derivative of f with respect to x, okay, is basically given by this concept of limit. Okay, this concept of limit, where we simply change the value of x by h, and then we make this h to be as small as possible. And what about y? We're going to simply treat y to be constant. Okay, to be constant. Okay, so this notation, okay, to make it simple, usually we denote the partial derivative with the this sub, okay, f sub x, okay, symbolize the partial derivative of the function f with respect to x. Okay, um, so in general, the partial derivative, okay, now with regard to y is the same. Okay, so we put f sub y. Okay, f sub y symbolize basically the partial derivative of the function with respect to with respect to y. So let's have a look at this example 1. Okay, so we have this function 2x squared minus 3x squared y plus 5y plus 1. So find the partial derivative of this function z with respect to x. Okay, with respect to x. So how do we do this? We simply need to differentiate with respect to x, holding y constant. Okay, so how do we do this? So let's just try to do this together. So the partial of z with respect to the partial of x. Okay, so this basically f sub x equals, there is an x here, so this becomes 4x, right? 4x, 2 minus 1 is 1. And then we're going to have, so treat y as a constant. So you simply put, we're going to simply put 3y, and then we differentiate x, so this becomes 2, right? 2x, and then this is 0, there is no x here, and there is no x here. So this becomes 4x minus 3 multiplied by 2 is 6xy. Okay, 4x minus 6xy. Okay, so that's how we do example 1. Okay, when we are asked to find the partial derivative. Next example, okay, find f of x 2, 3. Okay, using the same example from part A. So we simply, so this is what we have solved from the previous slide, 4x minus 6xy. So what we need to do next is simply to substitute x and y with 2 and 3, as simple as that. So you get negative 28, okay? And sometimes you may need to apply partial derivative, the chain rule, okay, when the function is more complicated. Like in this case, this is exponential to the power of e to the power of x squared plus y squared. So how do we do this? We simply use the chain rule, where we substitute, okay, we replace x squared plus y squared with u. So when like we have done this before, so what you need to do, because this is exponential function, so e remain as it is, but then you need to multiply the function with the derivative of the power of e with respect to x. Okay, so treat y to be constant. So focus on this part. So when we differentiate this becomes 2x plus 0, because there is no x here. That's why we bring this 2x to the front here, right? Okay, as simple as that. And this one, to replace it, you just substitute 2 and 1. Okay, in this case, instead of x, now you are differentiating the function with respect to y. So you have 2y e to the power of x squared plus y squared. Then to find the final answer, you simply need to substitute x with 2 and y with 1. You should get the answer. 2 multiplied with e to the power of 5. Okay, I'm going to leave example 3, okay, to you. I mean, this is the profit function. So find the partial derivative with respect to x, and then substitute, plug in these values, and you need to interpret the results. Okay, basically marginal profits. Okay, this is example 4. This is a Cope-Douglas production function. Okay, and you have f of xy. So we have two goods, 15 to the power of x to the power of 0.4 and y to the power of 0.6, where x is labor and y is capital. So the partial derivative f sub x basically represent the rate of change of productivity with respect to labor. In other words, they are called as the marginal in economics. It is called the marginal productivity of labor, f sub x. Okay, when we partially differentiate the production function with respect to labor. And similarly, when we differentiate it with respect to y, which is capital, it represents the marginal productivity of capital. Can we do this? Okay, why not? So if the company currently utilizes 4,000 unit of labor, so x equal 4,000 and y equals to 2,500, find the marginal productivity of labor and the marginal productivity of capital. Okay, for the greatest increase in productivity, should the company management encourage increased use of labor or increased use of capital? So in this word, we need to compare, right? We need to compare the marginal productivity of labor and the marginal productivity of capital. Which one would give us the highest increase in productivity? Okay, so So this is the original production function. So how do we find the marginal productivity of labor? So this one we need to find F sub X. So this equals, so we have 15. Multiply with, differentiate with X. I mean, differentiate the function, okay, with respect to X only. So we have 0.4. Multiply with X. So 0.4 minus 1 would be minus 1, and then multiply with y to the power of 0.6, because y, we are treating y to be a constant, so leave it as it is. So this becomes 15 multiplied with 0.4 is 6. X to the power of 0.4 minus 1 is negative 0.6 multiplied with y 0.6. Okay, and this is our marginal productivity of labor. And to find this, okay, to find the answer currently, so we simply substitute, okay, f of x sub x, where x equals 4,000, y equals 2,500, into this function. So 6, don't have enough space here, 4,000 to the power of negative 0.6 multiply with 2,500 to the power of 0.6, and this will give us, so use your calculator, okay, and you should have something around 4.53. 4.53. Okay, 4.53. So this is our marginal, the marginal productivity of labor currently. Now, the marginal productivity so similarly do the same for capital, and this is the marginal productivity of capital, and then substitute the values, and we get 10.86. So this is the marginal productivity of capital. Now, when we compare these two, so the MPL previously was around 4.53. So we compare these two, okay, MPK, okay, marginal productivity of capital and marginal productivity of labor. Which one is higher? Marginal productivity of capital. So in other words, capital is more productive. Capital is more productive. In this case, the management of the company should encourage the increased usage of capital. We should have more capital because it would have more, it would have more it would have more increase in productivity, okay, more output. Okay, the next concept is the second order partial derivative. What is this? This is basically we simply differentiate the derivative one more time, just like the second derivative that we have done before. Okay, so this function z equals f of xy, x to the power of 4, y to the power of 7, basically has two first order partial derivative, where we first differentiate it with respect to x. F sub x equals 4x to the power of 3, y to the power of 7. And then we have f sub y, which equals to 7x to the power of 4, y to the power of 6. Right? Okay. Now, each of these partial derivative, okay, has two partial derivative called second order partial derivative. Okay. So previously we have basically, so we have, okay, from previous slide. So this is 4x 3y7. F sub y is 7x 4y6. Now, each of these, they will also have two more. We can differentiate this with respect to x and y again, right? And this gives us the second order partial derivative. The second order partial derivative, for instance, f sub of xx. So what we need to do, we simply need to differentiate this with respect to x again. So 3 multiplied by 4 is 12. X to the power of 2, treating y to be constant. 12x squared, y to the power of 7. Okay. And we can also differentiate this with respect to y. So here we have 7 multiplied by 4, we have 28. X, treat x as a constant now, and then y to the power of 6. Okay. So similarly, for f sub y also would also have two second partial derivative. Okay. So this is the definition of the second order partial derivative, where we simply need to differentiate the first derivative again one more time, since the function consists of have two independent variables. So each partial derivative would again have two second order partial derivatives. So in other words, we have a complete set of four. Complete set of four second order partial derivative. Okay. Now, for this course, we're going to simply consider these two to be the same. Okay, they are the same. So in other words, we have basically simplified, okay, your work to be, you only need to find three. Basically, if such question come in the final exam, because we have already assumed these two to be the same, okay, and so basically you only need to find three pairs of second order partial derivative. Okay, this example, I'm gonna leave this to you, okay, because what you need to do is simply to differentiate them twice. Differentiate them twice. Um, and that's basically it. Or maybe we can do this together. Let's see. Yeah, why not? So this is simply asking us to find f(y)(x) of 2 and 1. So for this one, so first of all, we need to differentiate with respect to y. So look at the order. So f sub y equals, so there is no y here, so this becomes 0 minus, so we have a y here, so 2x, and then I have a y here, so I'm going to put 3y squared plus 0. Okay, so my f of y, f sub y equals negative 6xy squared. And then I need to differentiate this with respect to y, f sub y, and then x. There is an x here, which is to the power of 1. So this becomes negative 6y squared. And now I need to substitute this. So what is my f y x when x equals 2, y equals 1? So negative 6, 1 square equals negative 6. Okay, negative 6. And that's it. So that's basically the end of this part. Okay, and I hope you should be able to familiarize yourself. Just pay attention to the ordering of the sub, okay, at F, okay, whether you need to differentiate with respect to X first or Y first, okay. Just do them, one by one. Be careful, do not do any mistake. And whatever formulas, shortcuts that you can apply to make your derivative, your differentiation easier, so please apply them. So that's all for now. Thank you. Assalamualaikum warahmatullahi wabarakatuh.